Other questions? Maybe this is a good time, given the boot noise, to put your cell phones on stun. Yes. Okay. Question.
Yes. Actually, I have a question about the scatter plot.
Mm-hmm.
Let's say you have a line looking one like the dots, and then it's kind of homoscedastic, but you also have outliers, like goes up and down the graph. So does it still considered to be a linear association, or?
So the question is, if you have a scatter plot that's homoscedastic but has outliers,
Yeah, sure. Like,
then is that still
considered to be a linear?
linear? So linearity, I mean, maybe we should look back at a previous example to see if we can find. So this is an example of nonlinearity, right? It's sort of that basically you have curves, not something that generally follows a straight line. That's an example of heteroscedasticity where, depending on where you look, the scatter is greater or less. Outliers are typically one of two kinds, either something that's very far from the bulk of observations or something that is different from the general pattern of the observations. Now, I'm not quite visualizing what you have in mind. From what I understood from what you were saying, you're picturing something where sort of most of the points are sort of like this, but then you have an odd point like that.
More than one, like maybe 5 or 6.
5 or 6? Okay, well, so at some point, when it's enough of the data, it's hard to think of it as an outlier, right? It's just an indication that there's more scatter, right? Somehow outliers have to do with not being part of the general pattern of things. But if something like this still, to me, looks fairly linear. If what you saw was something like this, where you have a pattern like this, and then you have some points going up this way, that's starting to look like an indication that things are nonlinear over the larger scope, linear in some restricted range. An extra point or two out here doesn't change the linearity issue. Okay.
But it's going to change to heteroscedastic, right?
Well, at some point, I mean, so the question is it going to change? Is it going to become heteroscedastic? It's like at some point, if there's a lot of points that are sort of outside that general pattern, in a band of values of x, then this starts to look like heteroscedasticity. But an occasional point that isn't near the bulk is actually kind of to be expected, because this way I'm sketching this cigar, it's kind of capturing the bulk of points. But if you have a standard deviation, most of the points are in some narrow range. A few trickle out just by chance, as it were. We're not really talking about probability models for the data yet, but an extra point here or there is somehow to be expected. Other questions? Okay. We are going to talk about regression today, which is probably the single most misused tool in statistics, I would say. All right. To talk about regression, I'm going to start by talking about something that isn't regression in order to define regression in contrast to this thing. So we're going to start by talking about the SD line. The SD line is a line that goes through the point of averages, and its slope is that it goes up by 1 SD of y every time it goes over by 1 SD of x. So remember, this box is looking at the point of averages plus or minus 1 SD of y plus or minus 1 SD of x. So a line that goes through the point of averages and goes through the corners of this box has a slope of 1 SDY per SDX. So the slope is SDY over SDX. Okay. Now, the SD line is defined so that if the correlation coefficient is positive, you go up by 1 SDY for 1 SDX. If the correlation coefficient is negative, you go down by 1 SDY for 1 SDX. So it would be just the mirror image of this. It would go down instead. All right, so this is the SD line. It is not the regression line, and we're going to look at what the difference between those two things is. Question? You good? Right. Here's the GMAT data with quantitative GMAT plotted against verbal GMAT, and the purple line is, again, the SD line. So I'm going to put the SDs back on so you can see that it goes through the corners of that box. Now, the yellow squares are something new. Oh, so first of all, notice we've got a new concept. We now have a new button, right, the SD line. And typically when there's a button, the button says what will happen when you push it. So now it says SD line. If I push it, there will be an SD line. Now it says no SD line. If I push it, there won't be. So that's the usual story here. All right, we also have these yellow squares, which are the graph of average. So we can turn those on and off. All right. What is the graph of average? Well, it's taking a range of values of x and plotting the average values of y in that range of values of x against the midpoint of that range of values of x. So this range of values of x might be from here to here. The midpoint is this, and there's only one datum in that range. So the average of the values of y for that datum is just the value of y for that single one. So this is plotted at the same height as that. When we get over to here, then we're looking at a range something like that. This is the x coordinate of this square is the midpoint of that range, and the y coordinate is the average value of all the values of y in this little slice, in this range. Okay? So if you were going to guess what the value of y was corresponding to a point that had a value of x in this range, a good guess might be the average of all the values of y for all the data that are in that range. Right? It's a reasonable thing to do. Right? In fact, we know that it's, in some sense, an optimal thing to do. When we talked about how the mean, the median, and the mode were defined, they were each defined as the solution to a little optimization problem. The mean says, of all those points that I could guess, which one, on average, is the closest to all of the points, where closest means the square of the distance. So the mean minimizes the sum of the squared distances, some of the squared deviations. So if all I knew was that I was talking about a point in this range, and I said, the x value of the point is in this range, what's your best guess of the y value? A reasonable notion of best guess would be the average of the y values for all the points that are in that range. That is the y value of the point of the graph of averages here. Okay, so in each slice, the graph of averages has as its x coordinate the midpoint, and as its y coordinate the average of the values of y in that little range. Question? How do you choose the range of x values? It's arbitrary. This is, again, just an illustrative tool. It's a piece of scaffolding to get us to define the regression line. We're not going to use it as an independent thing. It's just to help understand what's going on with regression. All right, so if you look at this SD line, which goes up by 1 SDY every time it goes over by SD of x, is systematically off from the graph of averages. Right? It's way too low when you are to the left of the point of averages, and it's too high when you're to the right of the point of averages. Right? It systematically overshoots on the right. It systematically undershoots on the left. Okay, so this SD line is not a good representation, not a good summary of the data. What we want, if we wanted to summarize the data, if we wanted to say, I want to represent the data by a line in such a way that the y coordinate of the line for a given value of x is a good guess of the y coordinate of the data that are near that, of the data that have a value of x near that point of x, near that value of x. Did I garble that sufficiently? Let me try that once more. Suppose I have the challenge of finding a line that represents this point cloud, represents this scatter plot well. And we're going to talk more precisely about what well means momentarily. But loosely speaking, what I would like is to find a line so that for any value of x, the value of y on that line corresponding to that value of x is close to, as close as possible to, the values of y for the data that are near that value of x. Right? So if I wanted to find such a line, that line would not have as steep a slope as the SD line does. It would be shallower. Right? It would be higher on the left if it wanted to match the graph of averages, and it would be lower on the right in order to match the graph of averages. How much lower? This line has slope 1 SDY over SDX. What slope corresponds to a line that more or less goes through the graph of averages? And the answer is the slope of that line is R times SDY over SDX, where R is the correlation coefficient. Okay, so there's a very simple relationship between the slope of the line and things we already know about, the correlation coefficient, the standard deviation of y, the standard deviation of x. So if we had a line that went through the point of averages, makes sense to go through the point of averages, right? Because that is the overall average value of y and the overall average value of x, right? But when you went to the right, instead of going up by a full SDY, when you go over by 1 SD of x, it only goes up by R times SDY when you go up by SDX, when you go over by SDX. So R is never bigger than 1. Going up by R is going to go up by R times SDY will take you up not as far. Okay, in particular, R is 0.35. So when I go over by 1 SDX, I'm going to go up by about a third of SDY for this graph. Okay, so if that's a full one, this is about a third. It's going to come pretty close to that point on the graph of averages. So far, so good as a heuristic. All right. All right. So here is the same plot. Now with the purple line is still the SD line. Let me put the SDs there so you can see that it goes through the corners of that box. And the green line is now the regression line. The regression line is a line that goes through the point of averages, and its slope is R times SDY over SDX. So every time you go over by SDX, you go up by R times SDY. Okay? If R were negative, going up by R times SDY really means going down. Right? So the line would slope down. Right, this line does a pretty good job of going through the graph of averages. It misses over here where there aren't very many data, et cetera. But the graph of averages is kind of sometimes above, sometimes below, not systematically different. The regression line does a pretty good job of capturing the overall pattern of the graph of averages. Okay. If we have a football-shaped scatter plot, then the graph of averages for that plot will more or less follow a straight line. And that straight line that it more or less follows will be the regression line. They're all going to sort of coincide. Okay. If we had a scatter plot that showed nonlinear association, so things were kind of S-shaped, what's going to happen to the graph of averages? Is it going to follow a line? No, it's going to be S-shaped also, right? It will be, you know, if we had something that looked, you know, sort of like this, then when we constructed the graph of averages, it might look something like this. And no single line is going to do a good job of representing the graph of averages. Okay? So the regression line might end up looking something like this, and it's not going to do a very good job of representing the scatter plot. If we have a football-shaped scatter plot, and again, this has got a little bit of heteroscedasticity, the scatter's a little bit higher on the left than elsewhere, but generally, if the scatter plot is football-shaped, the graph of averages will approximately follow a line, and the regression line will be that line. That basically the regression line will come close to going through the graph of averages. Okay. Are there questions about this so far? All right. This has all been very hand-wavy so far. I want to make it a little bit more quantitative. What exactly does the regression line do? Let's suppose that we have a scatter plot. Let me put it this way. We've got a scatter plot. And here's a line. It's not necessarily the regression line. It's just some line. Right? A vertical residual from this line is the distance between, it's this difference, the y value of the point minus the y value of the line for the same value of x. So this vertical residual is positive. Okay? This vertical residual is negative. Okay? It's again the y value of the point minus the y value of the line for the same value of x. This is a vertical residual. All right. We could summarize the overall size of the vertical residuals from this line by taking their RMS. That's a way to get sort of a one-number summary of how big a list of numbers is, right? We have the original values of y for all the data. For each value of y in the list of data, we could subtract the corresponding value of y for the line at the same value of x. That would give us another list of numbers. And we could ask, how big are those residuals? How big are those vertical residuals? Well, one measure of how big they are is the RMS. What's the RMS again? You take the residuals, you square them, you average those squares, and then you take the square root of the result, root of the mean of the squares. Okay? Now, for different lines, the RMS of the residuals is going to be different. If I had drawn the line down here, we're going to have a whole bunch of big positive vertical residuals. The RMS of the residuals is going to be really big. Yes? If I drew the line, like this, it would be bigger than it is for the line that I'd drawn before. Right? The line misses the points more. All right? I'm going to ask, among all lines that I could draw, which one has the smallest RMS residuals, RMS of the vertical residuals? Okay? And the answer is the regression line. The regression line is the line for which the RMS of the vertical residuals is smallest. So this is a little piece of calculus, which I'm not sure I want to drag you through, but let me just set it up at any rate. So suppose I have a list of points xi, yi, and here I is going to go from 1 to n. I have n points in all. Okay? And suppose that I propose a particular line as a summary of the data. I could write that line. I want to make sure that I'm using the same symbols as I did before. Okay, got ax plus b. All right. So I might have a line that says y is equal to a x plus b. So the ith residual, we'll write it as ei. Ei is equal to yi minus a xi plus b. Right? This is the y value of that ith point, and this is what the line predicts the y value of that ith point to be. That's the value of y on the line corresponding to the same value of x. Okay? So what is the RMS of the residuals? It's, not sure where to go here in terms of board space. Maybe I should blank this for the moment. That doesn't work. Does that, that doesn't affect the out. And our inherited wisdom here. Okay, so what is the RMS of the residuals? Well, it's first we take the residuals and we square them, right? Then we average those squares. So we're going to take the sum from I equals 1 to n and divide that by n. Sorry, I'm using lowercase n or capital N. Let's decide on one. I'll make it a capital N. Okay, and then it's the square root of that. Right? That's the RMS of the residuals. If I want to make this as small as possible, it's equivalent to making this as small as possible, right? Square root is a monotone transformation. If I minimize the square, I minimize the, the square root. All right. What is this? This is 1 over n times the sum from I equals 1 to n of yi minus axi plus b squared. Okay. So far, so good? Suppose I want to minimize that. I want to now find a and b to make this as small as possible. You guys done problems like this in calculus? No. Wait, is calculus a prerequisite for this class? Yes. All right, I'm not sure I want to spend class time on this. It's in the book. You're not going to be required to derive anything like this. It might not be helpful. But basically, the minimizing value of a and b are given by the slope and intercept of the regression line. Let's figure out what they are from the fact that the regression line passes through the point of averages and has slope r times sdy over sdx. So we already know what a is. A is the slope of the line. It's r times sdy over sdx. And we want to figure out what b is, what the intercept is. Okay. Actually, just before I give up on this, is there anybody who wants to see the derivation of this? Yeah, that's what I figured. Okay. All right. Okay. So let's figure out, not by solving this optimization problem, but from the other characterization of the regression line, what the slope and intercept are. All right. So the slope A, I already asserted, is r times sd of y over sd of x. How do I find b? All right. We know that there's a variety of ways of specifying a line. You can specify the slope and the intercept. You can specify 2 points that are on the line. Or you can specify 1 point that's on the line and the slope of the line. Those all work, right? Everybody remember this from somewhere? I don't know where I remember it from, but I remember it from somewhere. Okay. So if we know what the slope is, we know one other thing, which is a point on the line. Namely, which point do we know is on the line? The point of averages. Okay, so we know that if you plug in y equals the mean of y, the average of y, then we should find that a times that value of y, let's go around the other way around. If we plug in x is equal to the mean of x, then we know that the slope times this value of x plus b should give us the mean of y, because this is a point on the line. Okay? So let's just do that. So mean of y is equal to r times s d y over s d x times the mean of x plus b. Now we're tasked with the giant conceptual problem of solving that for b. Okay, so b is equal to Did I do it right? Okay, so the slope of the regression line is r times s dy over s dx. The intercept of the regression line is what I just wrote on the other board. Mean of y minus r s d y over s dx times mean of x. Okay. If you like to think about lines in terms of slopes and intercepts, go for it. But it's a lot easier to work with the regression line if we think about things in standard units. So another way of characterizing the regression line is that y in standard units is equal to r times x in standard units. It's predicted to be, right? This is so if we measure y in terms of values in terms of standard units, then we would predict the value of y for a given value of x to be r times that value of x if we convert that value to standard units. So let's just see that this is actually the same thing. So I'm saying that this is the equation of the regression line in standard units. Right? What is it asserting? What is x in standard units? So I'm saying that something is approximately r times what? X minus the mean of x over the SD of x, right? The x in standard units is how many standard deviations above the mean x is. So we look at how far above the mean that is and find out how many standard deviations that is. This is x in standard units, and that's saying that this is approximately y minus the mean of y over the SD of y. Okay, now I'm playing a little bit loose and free with uppercase y's and x's and lowercase y's and x's and measured values and predicted values. So I just want to make sure that we're all completely clear what I'm trying to express. The regression line, the height of the regression line corresponding to a particular value of x is what we're talking about. Okay, so for a particular value of x, what the value of y for that regression line is this. So if we take that value of x, we subtract the mean of the values of x in the data, divided by the standard deviation of the values of x in the data, multiplied by the correlation coefficient of x and y in the data, then the corresponding height of the line would be this many standard deviations of y above the mean of y. Okay? That might not go through any particular value of y corresponding to a datum, right? This is somehow a prediction. It's a summary. It's the height of the line. This is not the data itself. All right, so is this the same as this? I claim it's the same line. Well, we ought to be able to do some algebra so that we have y on the left-hand side and some stuff involving x on the right-hand side, right? So let's just do that. We're not going to take this any further at the moment. I'll erase that. So starting with this, I multiply both sides by s dy. Okay, that gives y minus the mean of y on that side. And let's just rearrange things. So I've got y minus the mean of y is equal to r times s dy over s dx. I'm just taking the s dx out of the parentheses times x minus the mean of x. So far, so good? Okay. We're going to add the mean of y to both sides. That's easy enough to do. Okay. And now what I want to do is multiply this through the parentheses. Okay, so I'll get r s dy over s dx times x. That looks a whole lot like a times x, yes? And then I have mean of y minus r times s dy over s dx times mean of x, right? Which is exactly b. Should I write this down, the missing steps, or is it clear to everybody? Let's just multiply it out for grins. The only problem is my board discipline is not so great, and so we're okay. So this is equal to r times s dy over s dx times the mean of x plus the mean of y minus, so I'm taking this term, that times that, and tacking it on the end. It has a negative sign in front of it, minus r s dy over s dx mean of x. Okay, and so then we can see that this piece really is equal to this, and this coefficient really is that. So it's one and the same line expressed two different ways. All right, and then I've asserted boldly without proof that in fact this value of a and this value of b gives you that line for which the sum of the squared vertical residuals is smallest. So for that reason, the regression line is also called the least squares line. It minimizes the sum of the squares of the vertical residuals. It has the least sum of squares among all lines. Questions?
I don't get how that equation works though. Like y in standard units is almost equal to the r times x in standard units.
Well, the question is this like almost equal to, what I'm really trying to say is y in standard units on the regression line is equal to this on the line. So this is the equation of the line. This is the equation of the line. And then whether or not this is true for the data depends on how scattered the data are, whether the data actually have a scatter plot that's football shaped, and things like that. So really, this is the predicted value of y is equal to that. The value of y on the line is equal to this. Other questions? Like, when do we get our break? Yeah, that question. Okay, why don't we take a break for a minute and a half? It looks like I made an algebraic error in what I just erased. So let me fix that. What we should have is that y is equal to r s dy over s dx times x. And I think I had mean of x there instead of that, right? And then that's plus mean of y minus r s dy over s dx mean of x. Okay, and this piece is A, and this whole thing is B. And I think what happened is that I somehow multiplied r sdy over sdx times x minus mean of x and picked up two terms with mean of x instead of one with x and one with mean of x. So this is the peril of doing algebra at the board. Okay, so this is where we should have ended up. I apologize. Other questions? Okay. This is incomplete trash. Get rid of it. All right, so my recommendation when you are working with the regression line to try to figure out what value of y corresponds to a given value of x is that you work with it in standard units. It's just much, much easier to say predicted value of y in standard units is r times the measured value of x in standard units. That's a lot easier than figuring out what a and b are and plugging them into the formula and so forth and so on. I would just, my recommendation is keep it conceptual. You're much less likely to make a mistake. Okay, so for the regression line, just to say it once again, predicted y in standard units is equal to r times the measured value of x in standard units. Yes?
Other question. Is there a reason why it isn't r times sdy over sds instead of like this r?
Well, when you convert to standard units, it's taking, it is, when we convert it to standard units, you're dividing by sdy on this side, and you're dividing by sdx on this side. When you multiply both sides by sdy, then this side ends up having r times sdy over sdx in it. So it's the measuring things in standard units is exactly taking those standard deviations into account. That's what the algebra that I just botched shows. Other questions? Yes.
You had it before. It was like approximately last time.
Well, it's that. So there's this distinction between the measured value of y and the predicted value of y. Okay. So the value of y predicted by the line. What value of y on the? What is the y value on the line corresponding to a particular value of x? And that's the regression line, and this is the value of y on the regression line corresponding to a particular value of x. Okay. Whether this value of y matches the value of y for a particular datum that has that value of x, you know, that's up for grabs. That's going to depend on how close the regression line is to the data. And that's going to vary point by point. It's going to vary for different scatter plots. We're going to talk about overall summaries of how well the regression line fits the data. We're probably not going to get there today. Okay. All right, so this is the equation of the regression line expressed in standard units. Let's see. Keep the computer on the table. Okay. What we've been talking about so far is regressing y on x. In essence, trying to predict the value of y from the measured value of x. We could also regress x on y, try to predict the value of x from the measured value of y. There's really two regression lines in standard units. So this is what it looks like to try to predict y from x. This is the regression line for y on x, but we could also regress x on y. It would look like predicted x in SU is equal to r times measured y in standard units. And let's just, since my handwriting is so terrible, okay, so if you want to regress y on x, you want to predict y from x, then your estimated value of y in standard units, that is the value of y on the regression line in standard units, is r times the measured value of x. And conversely, if you wanted to try to predict x from y, the prediction would be that the estimated value of x in standard units is r times the measured value of y. All right. Beware. If the scatter plot of x and y is not roughly football shaped, the regression line is not going to be a very good summary of the data. Okay? The other thing to be aware of is extrapolation. I could have a situation where the data are very football shaped. Things look nice, linear, homoscedastic, no outliers, so forth and so on. But I've only got data in some limited range, and I'm trying to make a prediction way over here. Okay, so let me just give you an example of that. How many of you have taken physics in high school or something else? Okay, you remember Hooke's law for springs? It says that if you take a spring and you press on it with a given force, the displacement, the change in the length of the spring is proportional to the force that you apply. The constant proportionality is called the spring constant. Okay, so that's a nice linear relationship. It says if I double the force, I double the displacement, so forth and so on. And that's true over some range of values. If I could do an experiment where I look at, say, length of the spring, and here I look at applied force, and I might find something like this. So the spring has some resting length, even when there's no force applied to it. And the more I pull on it, the longer it gets. And I get some nice football-shaped scatter plot. Okay? And then what happens when I hang a truck off of it? Right? I mean, there's a point at which the spring loses its stretch, and there's a point at which the spring breaks. Yes? Okay, so this relationship might hold here, but what happens if I apply a force over here may not follow the same pattern as the points where I've measured it, right? It might be that it becomes, in effect, infinitely long because it breaks, right? Okay, so the fact that the data follow a nice linear, homoscedastic, no outlier sort of pattern does not mean, and so regression ends up being a very nice summary of the data in here, doesn't mean that you should trust the value of the regression line out here. Okay. If you're trying to use the regression line to sort of fill in missing data, right? I measured it in this range. I don't have a measurement exactly here, but I'd like to guess what would have happened had I hung a weight off the spring at that level. Had I applied that much force to the spring, the regression estimate might be a good estimate. That's interpolation, right? Trying to guess what would happen out there is extrapolation, much, much, much harder to justify. All right, we've already done this equation of the regression line. There are some special cases. If the correlation coefficient is 0, the slope of the regression line is 0. It's just a horizontal line through the point of averages. Okay. Correlation coefficient of 0 means there's no linear association between x and y. And if the regression line is supposed to tell you, if I know that x is in a certain narrow range, what's my best guess of the value of y? If the correlation coefficient is 0, it's saying, well, it doesn't matter what the value of x is. It's not really telling you anything about the value of y, anything linear. And so your best guess of the value of y is going to be the same, no matter what range of x's you're in. Okay? And so what is that same? What's the constant? What constant would that be? Well, if best means minimizes the sum of the squared deviations, then it's going to be the mean of y. The overall mean of y is going to be the same as the mean of, more or less the same as the mean of y in each of those little vertical strips. If the scatter plot is roughly football shaped. If you have nonlinearity, you could do much better with a nonlinear prediction, but we're just talking about lines for now. If the correlation coefficient is 1, all the data fall on a line, right? You only get perfect correlation. Correlation 1 is if all the data fall on a line that has positive slope. In that case, the SD line and the regression line and the data all stack on top of each other. There's just one line to worry about. If the correlation coefficient is -1, then again, all the points fall on a line. That line has negative slope. The regression line goes through all the data. Okay. All that's involved in regression is 5 numbers. The mean of x and y, the standard deviation of x and y, and the correlation coefficient. So if you know those 5 things, you can plot the regression line. When those 5 numbers are a good summary of the scatter plot, the regression line is a good summary of the scatter plot. When those 5 numbers are not a good summary of the scatter plot, the regression line is not going to be a good summary of the scatter plot. Well, when are those 5 numbers a good summary of the scatter plot? The scatter plot is roughly football shaped, i.e., there's linear association, the data are homoscedastic, and there are no outliers. Okay, so that's the situation where regression and that 5-number summary really let you make a mental picture of the scatter plot. Knowing that is sort of knowing an awful lot about what's going on. If there's nonlinear association, the regression line doesn't match the pattern in the data. It's not telling you very much. Suppose I have a football-shaped scatter plot that looks kind of like this, and a football-shaped scatter plot that looks kind of like this. Okay? What's the difference between those as far as the 5-number summary is concerned? Well, these have the same point of averages. Okay. In one of these, the standard deviation of x is going to be the same, right, in this sketch. Standard deviation of y, okay. In this one, they're typically further from the mean of y. And what's going to happen to the correlation coefficient? It's bigger for the plot that's more concentrated, right? So that's how that will show up. So a line is a reasonable summary of both of these scatter plots, even though the residuals from the line are going to be bigger for this fatter scatter plot. Okay, but what information tells me that scatter from the line is going to be bigger? In this case, it's in those 5 numbers, what's telling me the difference between these 2 scatter plots is the SD of y and the correlation coefficient. Right? So by saying that a line is a good summary of the data, I don't mean that the data all fall on a line. I mean that those numbers tell me that the pattern overall is linear, and that I can get an idea of the data are not systematically different from the line. It's not a situation like, this, right, where a line is not going to, line doesn't fit the data well here, but it doesn't fit it well in a way that's systematic, right? The points are going to be too high in one region, too low in another region. Okay. For the fatter football-shaped scatter plot, the overall fit is about the same wherever you look. I mean, if you look in a little vertical strip, the scatter in a vertical strip is going to be about the same no matter where you are. And what tells you about how much scatter there is in a vertical strip is the correlation coefficient and the SD of y. Okay. So summarizing a scatter plot with the regression line does not mean that the line comes really, really close to going through. You can summarize it well with the regression line without the line going very, very close to every point. It just means that the differences from the line are not systematic differences. It's scatter, football-shaped thing. All right. This is kind of a plug and chug sort of thing, but let's do one example for the sake of argument. So let's suppose we've measured the heights and weights of 1,000 individuals. If we look at the scatter plot of weight versus height, it's roughly football-shaped. Making this up. Say that the average weight is 150 pounds with an SD of 20 pounds. Average height, 66 inches, SD of 3 inches. Correlation coefficient of 0.6. Okay. Let's use the regression line to estimate a few different things. How much a 66-inch person weighs, how much a 72-inch person weighs, how tall a 160-pound person is, and how tall a person is whose weight is 2 standard deviations below the average. So we're looking here at regressing weight on height, weight on height. Here we're regressing height on weight, height on weight. Okay. First of all, if human beings were just sort of homogeneous solids, would it make sense for our weight to increase linearly with our height? People like this. People like this idea. If I take a... okay, there's some joke about some former Soviet Union, some applied mathematician is doing some research on spherical bodies and so forth and so on, and he presents it to the lab director, and the lab director says, no, you must do applied work. This is theoretical work. And so he goes back and revises the paper and brings it back, and the opening sentence is, consider a spherical cow. Okay, so let's pretend that that as you got taller, you also got wider and thicker in kind of the same relationship. Then as your height goes up, your volume is increasing kind of like the cube, right? Not linearly. And your mass, kind of assuming we are roughly as dense as water, a little denser than water, your mass would go up like the cube of your height, not linearly with your height. Okay, so a model that says that height goes up linearly, that weight goes up linearly with height might be reasonable for some range of values to some level of approximation, but it kind of doesn't really make physical sense. Okay. All right. So how do we do this? We want to find out what's the regression line estimate of the weight of an individual who's 66 inches high. So if I want to do this in the simplest possible way, where I'm least likely to make a mistake, what I'm going to do is convert 66 inches into standard units, multiply that by r, and that'll be my predicted weight in standard units. So then I just need to undo the standard unit thing to get it back to original units. So what is that? What's 66 inches in standard units? Well, the average height is 66 inches. 66 inches in standard units is 66 minus 66 divided by the SD. That's probably going to be 0. I'm just guessing. But OK. So this is 0 in standard units. So the predicted value of weight would be 0 in standard units. 0 in standard units is the mean. So the predicted weight of this individual would be the mean of the weights, 150 pounds. So the regression line estimate of the weight of an individual that's 66 inches tall is 150 pounds. No writing required. All right, what about somebody who's 72 inches tall? Well, the SD is 3 inches. 72 inches is how many SDs above the mean? 2. OK. So 66 plus 2 times 3 is 72. So it's 2 SDs above the mean. So my predicted value of the weight, the regression line prediction of the weight of that person, would be r times 2 in standard units. Okay, what is R? R is 0.6. 0.6 times 2 is 1.2. So the predicted value of the weight of this individual is 1.2 standard units. What's 1.2 in standard units? It's the mean weight plus 1.2 standard deviations of the weight. So the predicted weight would be the mean weight, which is 150, plus 1.2 times the standard deviation of the weight, which is 20. Okay? 1.2 times 20 looks a lot like what? 24? Yep. Okay, so that'd be 174. So the regression line prediction of the weight of that person would be 174 pounds. All right, now we're going to do the regression the other way around. We want to predict the height of a person that weighs 160 pounds. 160 pounds is 10 pounds above average, right? 10 pounds is half a standard deviation. My predicted value of the height would therefore be R times a half, right? Because this value is a half in standard units. So a half of 0.6 is 0.3. I would predict that the height of this individual is 0.3 in standard units. What is that? Well, it's 0.3 times 3 inches above 66 inches. 0.3 times 3 is 0.9 inches. 0.9 inches above 66 inches is 66.9 inches. Okay? This is probably easier than working out the slope and intercept and trying to plug into that. I'm certainly less likely to make a mistake. Questions about this so far? And the final thing, if an individual weighs 2 standard deviations below average, what do I predict that person's height to be if I'm using the regression line? 2 times 0.6. I'm saying this is minus 2 in standard units. 2 standard deviations below average is minus 2 standard units. We've got minus 2 times 0.6 is minus 1.2. What is minus 1.2? It's 66 inches minus 1.2 times 3 inches. Okay. All right. Okay, this next collection of topics often confuses people. We're going to talk about errors in regression, and the word error means very different things in this chapter. So one kind of error is simply the fact that regression does not perfectly represent any scatter plot. Unless the correlation coefficient is plus or minus 1, the regression line doesn't go through every point perfectly. There is some scatter around that. And some people call the scatter the error, right? The residuals. Okay? The residuals are a kind of error. The regression line doesn't go through every point. We're going to talk a little bit about how to figure out how far off the regression line is typically from the points that it's trying to fit. How far off typically, by how much does the regression line typically miss the y values of the data? Okay. Second kind of error is regression isn't always the right tool for the job. Okay. Even if the data are heteroscedastic, if there's nonlinear association, if there are outliers, then regression is not going to be a very good summary of the data. It doesn't get those 5 numbers, correlation coefficient, the 2 means, and the 2 standard deviations, don't summarize the plot very well. Okay? In that case, regression is probably not an appropriate tool, not a good summary of the data. Then another kind of error is you can be in a situation where you have a lovely football-shaped scatter plot, and you calculate the regression line, and that's what you get, right? Oops. Okay, you made an algebraic error in calculating the regression line. That's a different kind of error. You literally made an arithmetic mistake. Okay? So we have regression line doesn't fit the data that perfectly, even under the best of circumstances, with the really exceptional condition of the r being plus or minus 1. We have the fact that regression might not be the right tool for the job. We have the fact that it might be the right tool for the job, but you might just blow the calculation. All right? And then finally, we have the issue of interpreting what the regression is telling us. And very often, people make a post hoc ergo propter hoc or cum hoc ergo propter hoc fallacy in thinking that regression is saying more than it really does. Regression is measuring association. It is not measuring causation. There are also fallacies related to ecological correlation, which we mentioned before. This notion that if you look at the correlation of averages rather than correlation for individuals, you tend to get a larger value. You can get a smaller value, but you tend to get a larger value. Right, so let's look at all of these things. Several of these are going to be easiest to diagnose, understand, see in what's called a residual plot. And so first we're going to introduce the idea of residual plot. So this is the notation I was using earlier today. We have a collection of points, except that this is using a lowercase n instead of an uppercase n to denote how many points there are. So we have these pairs of values, x1, y1, x2, y2, et cetera, on up to xn, yn. And what is the first vertical residual? It's the measured value of y for the first datum minus the value of y that's predicted by the regression line for the corresponding value of x. Okay, so in this plot, these aren't very good points, are they? Let's try again. So if this is the regression line, and this is, for the sake of argument, the point x, I, y, I, then this difference, y, I minus a, x, I plus b, is this little height. That distance is the ith residual. Okay. All right. What a residual plot does is, instead of plotting y against x, it plots e against x. It plots the residuals against the corresponding values of x. So you can think of it as saying, for each point in the data set, it subtracts from the y value of that point the predicted y value of that point, the prediction that the regression line would give. Okay? If the data had a correlation coefficient of +1, then the regression line would go exactly through all the data, and when we subtract the regression line, we would get 0. And our residual plot would just be a horizontal line at 0. Okay? The points would all fall on the x-axis. Okay? Generally, that's not what happens. Right. Here is a residual plot for the GMAT data. So what we've done is, from each quantitative GMAT score, subtracted the regression line estimate of the GMAT score based on the verbal GMAT score. Regression line estimate of the quantitative GMAT score based on the verbal GMAT score. So again, we have a new concept, namely the residual plot. So now there's a new button which lets you toggle from plotting the data to plotting the residuals. Okay, that's the SD line. Let's get rid of the SD line. Let's plot the regression line instead. So that's the regression line. These are the original data. When I toggle this to say plot the residuals instead of the data, this line is below, this point is below the regression line, so its residual is negative. This point should be below 0 when I toggle the plot. Okay? This point is way above the regression line. When I toggle things, it should be above 0 because it has a positive residual. So if we go to plotting the residuals, that's what happens. We're basically just taking the slope out of the data and taking the mean out of the data. So we're sort of subtracting the average value of y and tilting it. That's what the regression line is, right? It goes through the average value of y and it tilts things. That's it. Okay, so the regression line is supposed to, if you like, suck up the average value of y. And so the average value of the residuals, the average value of the vertical residuals, we average the e's, they should average to 0. If we compute things and the e's don't average to 0, we made an arithmetic error. We did not actually, these were not actually the residuals from the regression line, the residuals from something else. Okay? Because algebraically, if you did it right, the average of the vertical residuals is 0. Okay. Now, we'll get back to that momentarily, but meanwhile, I want to show you that it's easier to see whether regression is a reasonable thing to do by looking at the residual plot than by looking at the plot of the original data. Okay, so one of the things that's a red flag for computing a regression line, or red flag for regression being a good summary of the data, is if the data are heteroscedastic. If the data are heteroscedastic, regression is not an appropriate tool. This is what a residual plot looks like. Okay, so here's the original data. You can see that they're heteroscedastic. But when you go to plotting the residuals, it stands out much, much, much more. It's just easier to see it in the residual plot. Okay. So here's the regression line for those data. All right, so easier to see heteroscedasticity in a residual plot. Similarly, you can see that this is sort of a nonlinear pattern. It stands out even more in the residual plot. It's just a little bit more pronounced. Easier to see nonlinearity in the residual plot. Here's a combination of the two. So there, this is pretty clearly curved, and that's clearly got more scatter than what's going on nearby. But it's even more pronounced if you go to the residual plot. So typically, going to a residual plot helps you see issues with the bivariate data that would make regression not be the right tool for the job. That would be red flags for using regression to summarize the data. Okay, the residuals are going to show heteroscedasticity, nonlinearity, or outliers only if the original data do, right? But they will tend to show up in a more pronounced way. They'll be easier to pick off. All right. Now, I mentioned before that if you calculate let's forget about whether there's heteroscedasticity, nonlinear, or whatever. If you calculate the regression line correctly, if you do the algebra correctly, if you crunch the numbers right, the average of the residuals has to be 0. Here, if I look at the point of averages, this is a residual plot. I'm looking at the point of averages, and the y value of the point of averages is -5. Okay, that means the average of the vertical residuals is -5. Something went wrong. That's impossible. Okay? There's an algebraic error in calculating the intercept, at least, of the regression line. Okay, so this residual plot is an indication of a numerical error, a computational error, as opposed to bad judgment in using the regression line in the first place. Right? What we were talking about before was the residual plot reveals poor judgment. Regression is not the right tool. Here we're talking about residual plot revealing you did it wrong, right? You got the wrong answer. Okay, here that doesn't really look like a trend to me. What's going on here? If the residuals have a trend, that is, if these points don't look at like it's so much, what's going on, but generally there's a little bit of a slope up and to the right. It's not a very strong trend, but there's a little bit of a trend. The residual plot should not have any trend at all. If the residual plot has a trend, then the slope of the regression line was not computed correctly. Again, it's an arithmetic error, not an error of judgment. It's an arithmetic error. Okay. So the residual plot should be essentially just scattered horizontally. So here's a residual plot that shows a bunch of problems all at once. First of all, very clearly nonlinear, right? Regression is not the right tool for the job. Secondly, the mean of the vertical residuals is around 70. So something went wrong in calculating the regression line. There's an arithmetic error. Moreover, overall, if you fit a line to the residual plot, that line would slope up and to the right. There's an overall trend in the residuals. They tend to be bigger and positive on the right, smaller and negative on the left. So there's a slope to the residuals, which is another indication that the regression line was computed incorrectly, that there was an arithmetic error in calculating the regression line. Okay, so what we see from this is regression isn't a good summary of the data, and the regression line was computed incorrectly. Okay, two different kinds of problems. All right, this is probably as good a place as any. Just let me reload the page once, just so you can get one more example. Okay, what do we see here, just before you go? Okay, vertical average of the residuals is 0. That's okay. But there's still a trend to the residuals. Overall, they slope up. So again, the regression line wasn't computed correctly. And we have very clear nonlinearity, very clear heteroscedasticity, so regression isn't a good summary of the data.